Okay. All right. So we're gonna kind of on part three of dynamic memory management. Uh, the reality is it kind of touches everything. So we are digging into some special features of classes today that help us manage dynamic memory. But part of our lecture is really about some of these special features of classes. So we're getting into some pretty deep stuff here. This is kind of like the basement in terms of really digging down to understand what C++ is doing. But this is some of the most powerful stuff that we're going to cover today. It's somewhat abstract, but once you wrap your head around it, you sort of realize why people go crazy for some of the incredible things you can do with C++. It just gives you so much control. So bear with us. I've created a lot of extra material to help you with the lectures from this week. So there's some more Quizlets, there's some recorded voice stuff in these PowerPoints. Obviously, we're recording this whole video, so you can kind of just watch the video again. But hopefully there's just different ways that you can kind of access this information. So most of you did your try matrix from last week. So we're going to raise the bar on that a little bit. And we're going to add to our class, we're going to work on our try matrix class. We're going to actually add things that we're going to learn today, what we call our copy constructor and our assignment overloads. These are two new features we're going to learn about in designing classes that help us when we're copying things around, which happens more often than we might realize. And then we'll play around a little bit with const on Thursday. Const is a really important qualifier for a lot of memory types. It's used in a lot of professional settings. We don't use it too much in class because it gets pretty intense pretty fast, but we'll try to weigh into that a little bit and have that in our lab on Friday. Now, for next Tuesday, we have our quiz coming up. And so a lot of this is pretty dense, 17, 18, 19, not 20, but you'll want to practice those quizzes or at least look at the Quizlets, which we'll talk about in a second. And really, you should have everything by the end of today that you kind of need for the jigsaw. Really, probably already you can jump into this, but hopefully by the end of today, you'll kind of see the bigger picture. Just a little heads up, I'm working on grading. Thanks to everybody who got 4 in so far. I apologize for all of this random shuffle nonsense. Basically, every once in a while, they get rid of something in C++, and I kind of knew it was coming, but I kind of buried my head in the sand. So some of you got bit by that. So if you're seeing that your cases 4, 5, and 6 are failing, or you're just basically in Program IZ, you're getting a bunch of warning messages. Do your own testing, but otherwise you can sort of ignore that stuff. I'm going to have to rewrite that for my testme.cpp. For reasons I haven't quite figured out, the program, the part that I already put into main is not really working properly in the testme. So basically, I often use this idea of deterministic randomness. That's sort of like shuffling a card deck in a secret order and then knowing already in advance what all the random numbers are going to be. So I often use that in my unit testing to see if you and I get the same outcome, right? When I sort of test your code. So the moral of the story is I had been depending on this fancy little function to shuffle your deck in a very deterministic way by setting my SRAND, each time in my unit tests. And this is a really cool strategy because it means, oh, well, we can just see if things end up being exactly the same. But when they got rid of this, I could no longer produce the decks of cards that I had produced over the last couple of years from my testing. So all of that sort of determinism went out the window. So I kind of, got by for a really long time without this determinism ever changing. But when compilers change or when features go away, sometimes that determinism can change too. So I got a little bit burned by that. I'll try to fix that up for you guys and in our future libraries. But it's an interesting lesson, that we all can learn. It's like, this is a really cool technique, but sometimes when compilers get updated over many years, they change. And commercial companies experience the same thing. They will be very careful not to change their compilers that they use to release commercial software, because sometimes if it's a really complicated piece of software like a rendering system or a game, little changes in the compiler can have very big effects on the outcome of the program. And so you see people hanging on to older versions of the C++ compiler for a really long time because they're just terrified that the results might actually change. And that's kind of a little bit of what happened here more recently for us. So anyway, that's just sort of a side FYI. I'll try to take away the pain for everybody, but that's kind of why my grading has taken a little longer than I planned. So let's just jump back into our review. So remember last time we just kind of reintroduced destructors, and we said, they really just get called when somebody deletes dynamic memory or when something goes out of scope. And we can just print a message, but sometimes we got to do some cleanup. And many of you kind of saw that a little bit when we were working with dynamic memory allocation. So here we're just creating a very simple instance using the new keyword. So that means it's on the heap. So FPTR is pointing to a piece of memory that we delete with delete FPTR. We're not deleting the variable FPTR, we're deleting what it's pointing to. So that's a really important thing to remember. New gives us a pointer, delete processes a pointer, right? So it just gets rid of what FPR is pointing to. FPTR still hangs around, but it's when we delete this thing that we see the triggering of our destructor, okay? Now, other times we could also see it when a regular instance of a class goes out of scope, right? So this is an actual instance, not a pointer. And after this curly brace, that is also going to trigger our destructor because the automatic stack allocation gets rid of that instance, okay? So we talked about that a little bit last time. Hopefully that kind of rings a bell. Now, from now kind of through the end of the year, just as a service, I'm going to sort of have more and more of these Quizlets. You might find them helpful for quick, rapid quizzing. So most of them, if they say with audio, there's a recording, a little 30-second recording that explains why a particular answer is what it is. So if you're working in a Quizlet question set with audio, at least you can always go, hey, I don't understand why that's the case, and just click on this, and you should hear me sort of describing why that's the case. So it's just a nice little feature that Quizlet has, and I think all those things are still working reasonably well. So here are kind of the different sets that we have: creation and code matching, given, new, write, delete, type matching, and then this is probably the trickiest one because it covers all of our lecture today. So you can kind of go through these things, and you can do them in different modes. You can do learning mode, which is like a multiple choice thing, or you can try to write the answer. It's a way easier to do it in interactive multiple choice mode than in writing mode. But you can kind of just click into these things or join the class, and you'll be able to get access to all of them. But let's just take a look at one of the new ones we're adding here. So this is kind of a challenge. We say match the right-hand side dynamic memory allocation with a correctly typed left-hand side declaration, right? So if I see this piece of code, I want to say to myself, oh, what does X need to be for this to work? Well, we know that new gives us a pointer, so whatever X is, it better be a pointer, right? So this Quizlet is asking us to come up with the declaration of X so that's compatible with this usage here. So it's a little backwards, but in that case, we just say, well, we're creating a new integer and new gives us a pointer, so X really has to be int star X. And you could put a gap before the star or after the star or smush it all together. It really doesn't matter in terms of the way the compiler views it, okay? So that's kind of a good one to practice because I kind of throw everything at you that will be in the quizzes or on the final exam. So if you just hammer away on that thing, you're going to be in some pretty good shape, I think, for the stuff that's coming up, okay? And you can look at that in learning mode, or you can look at that in written mode, okay? Now, another one is if I give you a description of something that says, hey, the following code dynamically allocates an integer on the heap with a value of 5 and returns a pointer to an integer, assigning it to an existing variable x. So we kind of just saw this on the previous page. So you would write x equals new int 5. Okay. Now for our quizzes, those are going to be multiple choices or fill in the blanks. So Quizlet is a little bit harsher than the quizzes in write mode. It's like, I got to write that from scratch, right? So, but it's just, you can look at the answers and just, prepare yourself for that. It is a good way to warm yourself up to that syntax if you're feeling uncomfortable about it. And last time we talked about this idea of deleting two-dimensional arrays. So this is what a two-dimensional array looks like, believe it or not. And so if it's dynamically allocated, that is. So we have this grid with three items in a row that's pointing to these individual arrays, right? So these are kind of manually created like so and hooked up. So we said last time if we want to delete it, we got to delete the rows. And as many of you pointed out, I had a little bug in some of my software. I had left that out, right? So we're getting rid of all of those things. And then we get rid of that last thing. Okay. And then we should nullify that stuff just to be really safe. Okay. So just like we can do this with integers, we can do this with any instance of a class as long as that class has a default constructor. So we're saying, hey, create 5 tokens. So these are really just instances of the class called token that are sitting right there inside of that array. So it's not a pointer to a token, it's an actual token, okay? So that means that we have a pointer to a token. That's a pointer to a token, right? And the rest are just sort of hopscotching along there. And then our grid is a pointer to a token, right? 3 pointers to tokens, right? And grid itself is a pointer to a token, okay? So I know I won't go through all of that again, but hopefully, you can follow through this code. And then when we want to delete that, we just got to do just what we saw before. Go through all the rows and delete them one by one. And because we're not, like if this was something hanging off of there, we'd have some other code inside of here, like another loop that we need to do. But since there's really no other memory allocation there, all we got to do is just delete the whole row. So we go through there and then delete the kind of high level armature and we're out of there. But pretty similar to the other one we saw, okay? So those are things you should review. If that still, causes you a little bit of confusion, take a look at some of the sample code there or our last lecture and let me know if you have questions on that. Now for today, we are going to look at kind of making copies of things. So we'll just do a quick recap on our syntax for one-dimensional arrays and pointers, just to make sure we're all together on that. And then we're going to start talking about the difference between making a shallow copy and a deep copy. Anytime you start creating data structures and people out in the world are like, hey, I love your data structure. I want to be able to make a copy of it in code. Well, that kind of presents a little bit of a problem. And C++ just doesn't do it for us automatically, even though sometimes we might think it will. So we're going to need to learn about something called the copy constructor. It's just another kind of constructor for our class, and an assignment operator, which is kind of an overload for the equal symbol. So we've had overloads for plus and minus and times, but now we're going to learn about overloading the equal sign, which is really the assignment operator. So that is an important thing we need to be able to control when we actually make copies of things, and we'll explain why that is. And then there's a couple other ones out there called conversion operators. We'll see some side cases where those come in handy. But the primary ones that we need to know about as C++ developers are these two right here. Okay, and we'll study those pretty quickly. And then we'll also look at this thing called automatic conversion. When I started coding in C++, I started making some mistakes. I would say, instance of class equals 5, and C++ would be fine with that. And I was like, how is that even possible? How is that even working? And it turns out that C++ is constantly doing automatic conversion between different data types. We sort of see it when we work with integers and floats, but it also does it when you try to assign a scalar value like a 1 or 1.5 to a full instance of some class. So how does C++ do that, and how does it know what to do, and how can we control that? So we'll look at that as our last topic for the day, okay? And then I'll get us to our lab where we're going to write a copy constructor for our triangular matrix and an assignment operator. Okay, so we'll see what those things look like in our lab today. So here's what I'm talking about when I talk about making copies. So here's a robot class, and let's say I give it a name, and who knows what else it's got inside of there, but I'm calling that robot A, named original. And then I say, hey, I want a copy of A and I want to put it in B. So this is what it looks like when we call a copy constructor. It's really just a constructor for the robot, but the argument that we're giving it is another robot. And you might say, well, that's just a constructor, right? But it's kind of special because it's based on another robot entirely. So it's officially called a copy constructor, and it has to be allocated in a very special way for it to be handled properly inside of C++. But that's what we mean by making a copy. While we're constructing B, we're making it based on a copy of A. Okay, so thus the construction of a copy like that. And it turns out that these are pretty much the same thing. And I'll just put a little asterisk there to say, well, there are situations where they're not. But most of the time, when I say this, I'm doing this, okay? And that took me a little bit of while to realize too when I was first starting out. I was like, wait, what is this? I'm just saying, hey, I want A to be copied into B, but what is it really copying and how's that working? Well, it's most of the time doing this. And if you haven't written one of these things, C++ is going to write one for you. And that's why things like this work between two different instances, but they might not always work in the way you think. So we'll explore a little bit of the problems with that. Now notice that this is a different thing altogether, and we'll get to this too. But when I say B equals A, B has already been constructed. A has already been constructed. So this is not a copy constructor. This is our assignment overload. This is our class, either through our code or through C++ default code, figuring out how to copy all the attributes from A over into B automatically, okay? And if we don't control this process, we may get some bugs in our code, and we'll talk about what that is and when we want to do that, okay? So here again, this is me constructing a different robot or a person, right? And saying person B equals person P. Well, this is a person, right? This is a robot. So how do we convert from one type into another automatically? Well, the robot class needs to know how to convert from some other class into itself. So the class itself needs to have instructions baked into it on how to do that conversion. Otherwise, it will probably not work in our code. So when it works, it's a beautiful thing. It's like we get to write this really fun high-level code, making copies of robots and converting people into robots, but somebody has to do the work below all of that so that we can actually have that really fun kind of coding experience. So let's just do a recap of things we should know already. So when we're working with arrays on the stack, right? So here is a pointer, just a little illustration about some pointers and arrays and things. This is something we know, an integer pointer that's set to null, right? And here is a regular number, 3, not a pointer, of course. And so I can set my number pointer to the address of number 3 there. So we've seen that a few times. So that's our kind of first basic education on pointers. But it turns out that arrays are kind of like pointers. The name of an array is the address of the 0th item. And this 5 just tells me how many of those things are tacked on to the end of that. So when we say square bracket I, we are offsetting or hopscotching I away from the first position of the array. In other words, the address of the array, okay? Now, when we pass an array into a function, because it was declared as an array, not dynamic, just regular array, we're going to pass it in pretty much the way we see that it was allocated there. We'll see on the next page that's going to be a little bit different. But we could force that value to be converted into a pointer, and it's still going to act like an array. So these pointers to integers and these array declarations are pretty darn similar as far as functions go. So I could pass this array into that one, right? And I could use my range-based for loop to print it out, which is pretty cool, especially with an array, right? So if the array is like this, I can still use my auto I of nums, right? And I can also pass that array into this thing where this is not looking like an array, but C++ is going to let us do that because there's such a strong connection between arrays and pointers to what they hold on to, okay? So those are all little sneaky backdoor things that we can do with our regularly allocated arrays and integers. Notice there's not a single use of the word new or delete here. Okay, so that's a clue that everything's on the stack. Okay, so you can dig into that code if you kind of want to play around with that stuff. So dynamically on the heap, what's different, right? So here's me saying, okay, I'm going to create an integer and initialize it with a 3, kind of like a constructor, okay? This is on the stack, we said, but this is on the heap. So we're holding on to the address of that thing, and then we can nullify a pointer, dynamically allocate an array, all of that stuff we saw last time. Now notice that we cannot use a range-based for loop with dynamically allocated memory. That always causes me confusion. I'm like, I was sure this thing actually worked. But if we're doing it dynamically, we cannot use that auto I colon thing, okay? So all of our arrays have to be sort of iterated with this I equals 0 to something and then pull the value out with square brackets, okay? So thus all of the warnings that we can't use that, right? It's not like we did something wrong. It's just, it's a feature that we don't have available to us, okay? So you can compare these last two pages, but hopefully, you know, they start to make sense to you as sort of our fundamentals for working with these one-dimensional arrays, okay? So these are the main differences here in the way we allocate and access that information, okay? Okay, so let's talk with that all as our refreshed memory. Let's talk about what do we mean by deep versus shallow copies. And this is really going to go directly to kind of the architecture we're using for homework 5. So remember that a copy constructor is called whenever a new instance or object is being constructed, okay? So if I'm constructing or creating something new for the first time, that's when our copy constructor is going to be called. And there's a few caveats where maybe it's not going to happen, but we'll come back to that at the very end. Assignment is when an object has already been created, but we're copying over it from another existing object. So in this case, both things already exist. In this case, one of them exists and the other one's being constructed. So we'll look at the code for that. But normally when you're working in a class, if you got to build one of these things, you probably got to build one of these things, and you probably need a destructor as well. So this is referred to often as the rule of 3 idiom. It's like if you're going to do a copy constructor, you might as well just, do all the nice things, and now your class is going to behave very well. If we don't do any of that, I'll show you the default that C++ does for us, but sometimes it can cause us some problems because it's not very intelligent, okay? So those are called our system level copy and assignment operators, okay? So let's take a look at what we mean by a shallow copy. So this is kind of right out of our homework 5. So our homework 5, we're going to have something like a puzzle class. We're going to create an instance of it, and it's going to have a pointer in here that's going to be pointing to some dynamically allocated memory, okay? So we're going to have to create an array of pointers, and each of those pointers are going to point to some dynamically allocated tokens. So this is what you're going to be building in homework 5. So when I say, hey, that's great, I got puzzle 1, Now I want to make a copy of puzzle 1 and copy it in puzzle 2. What does C++ do automatically? So if we don't add anything else to our classes, C++ is like, oh, I'll create a P2, and then I'm just going to walk through all the data members and copy them over. But this is a pointer. The pieces array is just a pointer to some dynamic memory. So it's going to copy the address over there. And now puzzle 2 is pointing to the same dynamic memory mess that we're pointing to in puzzle 1. Okay. So these two aren't really fully separated. This is a very shallow copy. So it might be that you want puzzle 1 and puzzle 2 to share the same pieces, but some people might think that a copy means a copy, like they're completely separate. So C++ is not going to give you a deep copy. It's going to give you a shallow copy where it just copies across each of the data members from P1 to the matching data member on P2. And if some of those data members are pointers, then we may have some problems, okay? Because you can see what might happen. Let's say somebody deletes P1, and now we got some pointers over here that are pointing to some deleted memory, and we get lots and lots of crashes that way. So shallow copies are kind of frowned upon. So how do we as coders get in there and control what's going on when somebody tries to do something like that, right? How do we actually control that particular copy construction, okay? And so that's what we're going to study here. But this is what I would call a very shallow copy. Maybe it's okay, but a lot of the times it might not be what you want. A less shallow copy could be something like this. It's a little bit silly, but we could take control of this, be a little lazy about it and say, well, I'll make my own array here, but I'm going to borrow your puzzle pieces, okay? So it's still not a true complete copy. And I'm not sure in what scenario that would be a good strategy to have, but we can see these things like we have one unique, maybe these are students at college of Marin, right? And so maybe these are all unique students, but we kind of have some students in some arrays and some students in other arrays, right? So maybe there's a situation where we don't want to have duplicate students, right? But this would still be considered a shallow copy, okay? So some of it is shared, a lot of it's not. True copy would, of course, be something like this. If I were to say P1 equals puzzle P2 equals P1, I'm saying construct a P2, study what's over here, and completely duplicate it over here. That means that this constructor, when it's called, has to create all of these things. This is a lot of code. It's like, okay, I got to study all of this, make the array, copy all the tokens, wire them all up. There's a lot of magic that happens in there to make that really nice. But that's exactly what you have to do if you want to really have a true copy, and your class has to provide that capability. Okay. So the moral of the story is when we design the class, we got to think really hard about whether or not we need to kind of enhance the default system copy, assignment, and delete behaviors. If it's a really simple class with just some integer values, hey, just use the basic system level stuff. But when we get into dynamic memory management, we have to take control of those things and write our own versions of them. And that's what we're going to look at today. And that's what our Lab 19 is going to do for us, okay? So let's take a look at the copy constructor and what that is. So anytime we create an instance of any class, we'll call that our construction time. That is the opportunity for us to trigger one of our own constructors, a special overloaded constructor that handles copying things. So here is our default constructor for a silly little class called foo. So it's just going to say hello. It's not even really initializing val, which is kind of silly, right? So it's a pretty dumb class to start out with. But what if I wanted foo to be constructed based on a copy of some other foo? Well, I'd need to do something exactly like this. I'd need to say foo const foo ampersand RHS. So I'll show you what this RHS is, but it is another copy of foo. And we are not allowed to change that copy, right? but we can steal its value and put it in our own value and print a little message that says, hey, I just copied that, okay? So that is a copy constructor. So how do we trigger that thing? We would say foo f1, foo f2 equals f1, okay? So this triggers the copied message down here because this becomes the right-hand side of that equals, right? So F1 is the right-hand side getting passed into our constructor, and we're just sort of seeing it in a slightly different form, okay? This is different. That is not a copy constructor. We will get to that here in a few minutes. That's our assignment operator, okay? So this pre-exists and this pre-exists, so that is not a copy constructor. This is a constructor, this is a constructor, and this is copying from F1, okay? So we have to have the const, we have to have the ampersand. This declaration is very specific, but if we do it, then we will have control over these kinds of scenarios. Now, we are in control of what's going on inside of our copy constructor whenever something like this happens, okay? In fact, if we do something like, I guess I don't have it. I'll show you another version of this in just a second. But that's what we mean by a copy constructor. We just got to add a third thing to our class in addition to any other constructors or destructors. And now we have control over that situation right there. Okay. So let me just show you the code for that real quick while we're here. So I will do that so we don't blind ourselves. Okay, but you can kind of see, and this is what the Quizlets are helpful with too. It's like, okay, that looks like a regular constructor. That looks like a destructor. And down here is our foo copy constructor, okay? So you can see if I say F3 equals F2, it should trigger that copy message. In fact, this is also the copy constructor. These two things are most of the time the exact same thing, okay? So if this is 1 and this is 2, this should copy the 1 into the 3, and this should copy the 1 into the 4, okay? So let's just see if we get our messages on that one. So we get our hello from our regular constructor. We get our triggered message copying from the 2. And then the goodbye, right? The goodbye is coming because these are all going out of scope at the end of our main function, which is down here, okay? So you can kind of play around with that if you want, but that's the main idea with the copy constructor, right? We're just going to, we might do exactly what the default copy constructor is doing, right? That's all the default copy constructor does is it copies from one thing over into the corresponding value here. But there are lots of situations where we may want to do something different, okay? So again, this is this instance, right? And you can leave off this arrow for val if you want, but that val is from this instance, and RHS is the F1 here, okay? So it's a lot like our overloaded operators from earlier in the semester, okay? Now, just to point out, again, this is the exact same thing, right? So we call this direct initialization when we put the F1 directly inside the parentheses, okay? This approach right here is pretty much the same, and most of the time it's going to do the exact same thing. It's called copy initialization. Don't expect you guys to know the names to all these things, but when you see that one up there, you should think of this one right here, right? We're making a copy of something, and we're essentially most of the time going to trigger this copy constructor, okay? So let's consider a number class, right? So this actually, you might think, okay, this is pretty straightforward, but you'd be surprised at how easy it is to get disoriented. So here was what we're going to do. We got an instance of a number class, and its whole purpose in life is simply to keep track of a number, but we're going to give every instance a unique ID. And the way we're going to do that, it's a little bit, hacky, but we're going to pick a random number between 1 and 1,000, okay? Generate a random number, modulo 1,000, shift it by 1. So all of our instances should more or less probabilistically have a unique ID for just a couple of these examples, right? I would never do this in production code, but So now we have a unique ID, and when we destroy it, we can report which one we're destroying and what its value is. So now we have a way of determining whether or not our copy constructor is really working or not, okay? So it's going to help us keep track of copies, even though the ID should be different, okay? So let's take a look at how we add a copy constructor to this kind of class, right? So we actually do get unique IDs for copies, even though they might have the same value, okay? So let's see if we can do this one together and follow what's happening in main when we actually do this implementation, okay? So let's take a look at what we have. So we have our number class. It's got a unique ID and a value, okay? So when we create a normally constructed instance, we're going to give it a unique ID. We're going to give a little message and say, I'm this particular value, okay? So we're going to assign it I as its value. Okay, and then we'll have a destructor. That's fine too. But here's our copy constructor. All right, so how are we going to do this? So we want to assign a total unique random ID to this new thing. We don't want to copy the ID from this thing, right? So I'm going to say my ID, and you can say this or not. This is optional in this case. ID is equal to rand modulo 1000 plus 1, okay? So this brand new copy that we're constructing gets its own statistically unique ID, but we're going to pull the value from RHS. So I'll say this arrow val equals RHS.val, okay? So this is a pointer, and RHS is clearly not a pointer. It's a reference, right? So I'm just grabbing onto its value. And if I want to add a little help, I can say cout, copy from ID equals RHS dot ID into ID equals this arrow ID value. I know this is kind of long, val, okay, or RHS dot val, okay. I haven't copied it over yet, so I don't want to use my own val on that. NDL, okay. And then we do the copying, and now we're done, okay. So it's kind of annoying, but let's just sort of see if that thing runs, and then we'll explain the rest of this. So let's take a look at what is generating all of these things. So this is our regular constructor. This is our copy constructor, and here's this strange destructor being triggered in the middle of all this. So I don't remember actually kind of ever creating something, right, and then destroying it. So I wonder why that's actually happening. So we'll get back to what's happening there in just a second. And then, of course, we have all these other destructions. So let's go down to main and see what some of the basic stuff's happening, right? We set my random number generator. I construct N1 and N2, right? So that is N1 and N2, right? Values 1 and 2, right? And then I want to assign an existing instance of num to a new instance of num, right? So I haven't really done the part I wanted to yet. So let's say num N2 equals, well, let's first do it the maybe more obvious way. A copy of, sorry, N3 is going to be constructed based on a copy of N2, okay? So let's just see what that looks like, okay? So we're copying from N2, so that's 887 into our brand new 778, the value of 2, okay? So this is what's coming from our copy constructor, okay? But we're also getting this weird thing, right? Copy ID 384. So what is that all about? Okay. And that's ID 996. It gets created and then it just gets destroyed all of a sudden. Well, it turns out that even when I just pass this N2 into there, I potentially get a copy of the N2. Okay. I actually shouldn't. So there may be something else going on here that I'm not really tracking because this is a reference, so I shouldn't be getting a copy from that. But there's a little bit of a mysterious extra copy of something being created here that I'm not quite sure. It may be coming from down here, okay? But in any case, we are least triggering our copy constructor. And this is what we want to have control of, right? We want to be able to write code inside of there that actually allows us to control what's going on, okay? And so that's pretty much what we have over here, okay? So just remember that this is really the same as num3 parenthesis n2. So all the way over here in main, when I did this, I could have been saying equals n2, and I would get the same behavior, right? I'd still get my copy message happening, okay? So that's us taking over what's going on in that particular situation. And that's a really good thing because that's going to come up a lot of times out in the real world, okay? It's not going to be called for n1 equals n2, but if I'm constructing a brand new n1, then we'll actually get that thing called. And it is also going to get called in these situations. Okay, so this is a little bit of some advanced stuff. But if anytime you return an instance of a class, it's going to make a copy of it to return it. Anytime you pass it to a function without a reference, it's going to make a copy. And there are lots of other times when temporary copies get created. So one way people optimize their code is by controlling the copy constructor and minimizing the number of copies that are created. Okay? So we're not going to get too deep into that, but when we say that C++ is a copy-centric language, that means it goes copy crazy most of the time, and we might need to get in there and prevent it from doing some extra stuff, okay? Now, a lot of compilers will kind of try to optimize things for us. So sometimes where we might think a copy is going to occur doesn't occur because the compiler finds a way to borrow some existing memory and avoid the copy. So we won't get into that, those special cases too much. The high level stuff we want to remember is that the automatic copy that we get is a very shallow copy. And it's not going to work for things like our puzzle and homework 5. Okay, it's a very high level copy of all of the attributes, and it's kind of not really sufficient for really complicated architectures. Okay, but it does get called very often in these kind of scenarios. Okay, so we could write our own and control exactly what's going on there. Okay. Now, we can also come up with our own delete, right? So we saw with a destructor, we could actually do that. Oh, sorry, I'm on the wrong track here. If we want to take away the system level copy constructor to avoid accidental shallow copies, we can actually do that. And we'll talk more about that in the next couple weeks when we get into some special pointer stuff. Now, very advanced, don't worry about this, but some people dig into this and they come to me and they say, hey, Jeff, you taught me all that stuff and I'm not seeing that happening in my code. And that's because the compilers have this feature called copy elision or RVO, okay? I didn't make up these names, but what they mean is we're given the compiler permission to skip the copies whenever it is allowed to do so. And it turns out that copy elision has been actually recently elevated to be a requirement of many compilers. It's no longer optional. It actually is got to be turned on all the time, okay? So we can turn it off, for example, by setting a compiler flag, but most of the compilers now, C17 and later, are requiring it as part of the C++ standard. So the moral of the story is we can control the copying when it happens, but sometimes it may not happen as often as we think, okay? So again, you're not going to be tested on any of that, but if you do dig into the code, you might be a little confused, and that may be because we have this optimization going on at the compiler level, okay? So that is what happens when we're constructing new instances. What happens when we're copying an entire instance over the top of another instance? So here's us with an instance of my number class with value 1 and ID 121. And here's another one. By default, if I say n2 equals n1, it's going to copy everything over, the value and the ID. And now we got a problem, right? We have two students with the same Moodle ID, right? That's not good, right? I might have wanted to have the same, grades of somebody, or maybe if it's a car, I like your red car, so I want my car to be red, but I don't want the VIN numbers to be the same. So that's not a copy constructor, that's an assignment operator, because this already existed and this already existed. But it's the exact same problem we just solved. We've got this system level thing that's doing a very shallow copy, and we need to do something a little more intelligent, okay? So we're going to need to write a slightly different thing in our class that does pretty much the same kind of stuff. So let's take a look at how we do that. Here's our standard constructor. Here is our assignment overload. So remember when we say operator plus or operator minus, we are changing the behavior when a user uses that symbol with our class. So operator equals is just an assignment overload for the equal sign. So if somebody gives me a reference, const ampersand reference to a num class, I can then do what I need to do to copy stuff over. So let's say I'm just going to steal its value and print out a little message so we know that we triggered this assignment operator rather than something else. Okay. And then maybe I will return the pointer or the instance of this as a reference so that we can chain things together. And we'll show you what we mean by that. Okay. So we have a constructor and an assignment overload. And we could have a copy constructor in here too, but I left that out just for brevity on the slides. But here's how we would use that. Create an instance of 1, instance of 2, and say instance of 3, and I can say n1 equals n2. And that's going to trigger our code. Whatever we want to do in here, that's going to get triggered, okay? So n2 is going to get updated, and we can even do something crazy like this if we return a reference, right? So the only reason we're returning something here is so somebody can chain together lots of equal signs, which I don't know. I don't like writing code like that, but if you want to be really nice to your users of your class, you may want to actually do this and this right here, okay? But fundamentally, we're changing this by copying these members over in some special way, okay? So that's our assignment overload. And between the copy constructor and the assignment overload, we've now made our class a lot more intelligent. Okay, so let's add that thing to the following code here real quick. So we've got our num class started. Let's kind of dig in and see what this requires of us. Okay, see if I can get that thing to come up. You certainly don't want to be in Python. There we go. Okay, so let's just sort of scroll down here and look for the to-dos, right? So here's our default constructor, creates an ID, sets the value, kind of like we were seeing before. There's our default or our own destructor. Here's the copy constructor we just made a few minutes ago, right? So creating a new copy, right? Here's a new ID, steal the other value, etc. Now we got to do our overload. So let's just, uncomment that. It's got to be exactly like this, right? We'll uncomment our curly brace down there. We'll print a real quick message. So I'll just say cout assign from RHS from ID RHS.ID to this ID, okay, with value RHS.val. Okay, so that's what we're doing. Okay, so this has a value and an ID, right? And I have an ID already, right? Because I already exist, right? So I'm not creating a new version of me. I already exist. Okay. So let's do the assignment of the val. Val, this val, my val equals RHS.val. Okay. And then let's just return that reference, right? Turning a reference, dereferencing the pointer to get an instance, creating a reference. Okay, I know that's tricky. And then down below, we can just see if this triggers our assignment. Okay, see if I got it right. Okay, so creating, there we go, assigning from ID 384 to 87 with a value of 0. Okay, so this would not happen unless we were doing this. So if I take that out and I run it again, right, I just see creation and I see goodbye. And the goodbye happens when these go out of scope right here, right? Goodbye. Okay. Or we can bring that thing back in again. Okay. But that's our assignment of two existing things. Okay. So we're slowly adding more and more features to our class to handle these different situations. It's a little bit tedious to do it, when you're writing this stuff, but eventually you have a really nice class that can survive a lot of different use cases. So that is called our assignment overload. Okay. And so you can kind of look up the solutions. We have a Replit link there, but you can probably infer how to get your program IZ link with all the solutions in it as well. Okay. So sometimes returning star this does not trigger our copy constructor, and that's because of the reference, right? So if we are returning a reference, it's not a copy. It's an actual just kind of reference to an existing copy that's already there, okay? If we were to remove that from our code, so for example, if I were to take away this right here, we would see this trigger a copy constructor, okay? That would create a temporary copy just so we can return an instance for a brief moment in time, which is kind of wasteful, right? So that's why we put a reference there. So we're not really returning an actual copy. So there's a lot of situations where we might actually get a copy if we're not careful, which can be very expensive, right? If it's a really huge instance of something like a movie or a song, that's like for a split second in time, you've just made a 300 gigabyte copy of something and then you deleted it, right? So those are really painful things that happen if you haven't optimized your code. Pretty advanced stuff, but definitely the kind of control that most C++ developers like. Okay, so there's a third kind of assignment that happens, and it happens automatically. And it's in situations where somebody tries to assign one data type to a different data type. So here we have a num class with an integer value, okay? And I can create an instance of that, but I would like to be able to convert that thing into a character when somebody wants it. So let's say somebody tried to print an instance of numF. Well, what is cout supposed to do, right? Cout needs a string or it needs a character or something. So it looks at the class and goes, hey, can you convert yourself into something I need? And the num says, yeah, sure, I can give you my x, okay? So this triggers this conversion operator here and gives a representation of that instance, which is the case is just the letter X, right? Which is kind of silly. It probably should return the value there, right? But it's just the letter X, right? So that's one way of getting a class to convert itself into something else, okay? And there again, specifically, that's because the cout needs a string or a character in order to get that information out, okay? So let's take a look at something more realistic. So most of us have had to deal with complex numbers. So one way to get a complex class instance to print itself trivially is to just do that. Operator double, return the square root of the real part plus the imaginary part. So this is the classic, conversion of a complex number into its magnitude. So it's a vector magnitude, really. So if I say cout, C, my complex instance, it's going to trigger this and say, hey, what do you got? Cout says, what do you got that I can print? I can print numbers. I can print strings. I can't print a class I don't understand. So the class converts itself into a double And what we see is the magnitude of that complex vector. So that can be a really slick way to have your class instance be printable in some useful way. Okay. Converting that thing into whatever makes sense for the class. Okay. So these are called conversion operators, right? And of course, you can choose whatever thing you want to convert it into. Okay. In that case, we get our double. Now, if we don't have one of those provided, sometimes, once again, C++ tries to do the simple thing automatically. So we call this automatic conversion. So if I have a class that has a single value in its argument, like this, and I do this, n1, and then I try to assign an integer to what is clearly not an integer. How does C++ know what to do to make that work? Well, it's going to basically it's going to say, hey, I am just an integer and you have a constructor that just takes an integer. So I'm just going to call your constructor and create a copy and then call your assignment operator, right? So it's going to basically create an instance out of this and then copy it over that all automatically. Okay. So a lot of times people write this kind of code without even thinking about it. They're just like, oh yeah, I want n to be 10. And it's like, wow, how does that even work? Well, it's this automatic conversion that actually happens. Okay. But as you can imagine, we can control all of that. Okay. So let's see if we can actually kind of write one of these. So we're going to have a person class. And when we print a person instance, we want to actually have the whole thing convert itself into a collection of strings. Okay. So we're going to have to convert the age and the zip code of the person using the toString function. But otherwise, we're just going to concatenate a bunch of strings together and return them. Okay. So let's see if we can actually do this one together. Okay. And we don't have too many of these today. And we might have to, when we print this in main, say, hey, convert this into a string, which should trigger our string conversion method. Whoops. Let's go over here first so we don't spoil the ending. Okay. So here we go. Here is our person class, first, last, integers, right? Here's our constructor using our constructor initializer list. There's really no guts to our constructor there. So we want to convert this into a string, okay? So we're going to say string, because that's what we're converting into. And now we just need to return a string, right? So we could just say return foo, but that's not really helpful. So what we want to do is add together all of these things, right? Concatenate them into some kind of sentence. So I'll just say return first plus space plus last plus, and there's where things get tricky. I have to have the toString age, right? Plus a space plus toString zip code, okay? Right? ENDL. So, or no, not ENDL. We'll just leave it like that, okay? Okay. So we're cobbling together some information from our class whenever anybody needs a string, okay? So down here in main, let's create an instance of a person, Jeff. It's 21 years old. I live at 1313, or that's my zip code. Say 94904, okay? And I say, hey, give me a string version of that instance. That should trigger this conversion operator. Okay, so let's see if we get that printed out okay. Okay, looks like I forgot the capital C on my zip code. So let's go up here, up C, okay, and run. Okay, there we go. So that's our conversion operator. It asks the class, can you give me a string? And if the class can't do that, then it's going to fail, right? So if I were to obviously kind of comment that out and run it, we're going to get an error, right? Cannot convert to a compatible type. Okay. So there's our kind of implementation of that. So we could do a whole bunch of these, right? We'd have string, float, double. It all depends on what your class needs, what you think other people are going to want your class to be able to deliver to you. Now, sometimes adding all that stuff to your class makes your code kind of buggy because we don't really know when things are getting converted. So we can add the word explicit to prevent something from being automatically converted, right? So if I don't want this situation to work over here, I put the word explicit in there and it prevents that 10 from being silently converted into an instance of n. You might think, well, why would we want to take that away? Well, maybe that's, something we don't really want to encourage when people work with our class. Okay. So the keyword explicit is just out there to prevent abuse of that particular feature, or just kind of reduce the number of bugs that might occur in your code. Okay. So just keep that in mind. You can put it in front of anything to take away some of the functionality that happens automatically in your classes. So that's kind of it. That gets us to our lab. Let me just see if anybody has any questions about any of this stuff before I kind of jump into our copy constructor for our trimatrix. Yes.
So explicit gets rid of any overrides you might set for things like equals or.
Exactly. If you put an explicit in front of here, it means that you are disallowing any of the automatic system level things from taking advantage of that.
Is there any way to see from the outside without looking at the code if equals has been overwritten?
No, you got to look at the class. Yeah. Yes, exactly. Yeah. Some people don't like all of these extra converters because it means that you can actually accidentally, might not even know when you're converting something into some other data type.
Yeah, I feel like if you're working in somebody else's code base all of a sudden and you didn't know they did all these overrides.
Exactly.
Really be.
Oh, yes. Yeah. It's like, when you pass in a character into an integer argument for a function and it goes, oh, I'll just convert that to an integer, but you didn't know you were doing that. It's that kind of bug. Yeah. So it's a little controversial writing a lot of these converters, and you don't always do it, but it's just another example on how to control that. So let's look at our lab today. It really just brings these 2 points home for our trimatrix. Now, this is a little bit more of a complicated lab than it might seem. But if you can do this one, you're really doing okay with these topics. So here's what we're actually building, just to remind everybody what we're doing with our trimatrix class. So all this code is written for you. So you don't need to write the constructor. You don't need to write the destructor. All of that is handled for you already. And there's even a print me, and it's even going to initialize everything for you. So we've written a nice class that handles most of the possibilities, but we want to be able to make copies of this, like a true deep copy. So if I say something like, I don't know if I have the code on this page. If I basically say, B equals A, I want to have a deep copy of that thing. Okay. So here's what I want to be able to do. Here's B, right? That whole thing there. And I want to have A be a copy of B, and I want to have a deep copy. So that means you have to write the copy constructor. You have to inspect, B and figure out what to make. And you're going to have to rotate through all of these things to copy the values over exactly. Okay. So it's not like you're just going to construct A with the same number of rows. You got to copy all these values from all these exactly over into there. So there's a little bit of loops that need to be written for your copy constructor to actually make a deep copy of this. Okay. But it's worthwhile doing because you realize, wow, okay, that's not simple, but once you do it, you appreciate when other people do it for you in their classes, right? So similarly, we want to be able to do this. So here's me with two existing matrices, right? but I want to copy over A with B, which means I got to get rid of these properly. This is the one where everybody sort of falls off the rails. Not only do you need to delete these, right? Then you need to reconstruct them, okay? They might be different, okay? So a lot of people will skip over that and get memory leaks. They'll just sort of like write over the top of stuff when they do their assignment. But you got to delete A, then make a copy of B and assign it, okay, in a deep way. So that one is a little trickier than it looks, right? So don't worry if you don't get it right. I'll give you some hints when you kind of get to that part of the lab. But otherwise, those are really worthwhile doing. So here's just what it looks like in main. I create a triangular matrix, right? And I give it a certain row count of 5. I print it out, okay? Then I, prompt the user, see if they want to continue. And now we make a copy, okay? So that's our constructor. And we print it out. And then we kind of make another one. And then we do our assignment, okay? So this one has 7 rows. And this one has 5. So when we copy the 5 over the 7, it should get rid of the 7 stuff properly and then make a duplicate of the TM copy. Okay. And then we can print that back out. Okay. So that's our try matrix. So let's just look at the code real quick and then I'll let you guys get out of here if you got to go. So let me go back to the previous slide. Come on now. Then you can do this, by the way, you can do this lab in either the online compiler for Program IZ. You can do it in Program IZ Pro, or you can do it in Replit. So sorry for all the backing up here. Let me just get to my links here so I can jump into it. So in Replit or Program IZ Pro, you have .h's and .cpp's. So in order to enable using the online compiler, I just pulled the .h into here, right? So this is the .h, right? This is the prototype. So for those of us who remember the .h's, they don't have implementations for their constructors, but you can see the prototype for your kind of the blueprint for your copy constructor, the blueprint for your assignment operator, right? And then down below, I've implemented some of these for you out of class. So this is the equivalent of our CPP file, right? And so you should study your CPP file and your destructor to kind of know what you got to do in your copy constructor. Okay, I've laid out your copy constructor for you, but you got to fill in your code there, and you got to fill in your code here. Okay, but the rest of it is kind of done, right? So now in main, we just have that stuff we were just looking at, okay? So that is what we want to try to do. And I will leave you with that. And don't forget about your homework 4 if you're planning on turning that in tonight, okay? Well, thanks everybody. I'll let you get out of here and I will see you on Thursday.